On this episode of the Encrypted Economy, we have Rand Hindi of Zama.ai on the show. Zama.ai is working on enhancing a homomorphic encryption scheme known as TFHE to drive more throughput and increase encryption efficiencies. Its natural focus is artificial intelligence, but with the types of throughput efficiencies they are focusing on, it can apply across a variety of homomorphic encryption use cases. This episode is relatively short compared to some of my others, but you may need to listen to it twice, or even make sure you're not listening to it at more than 1 times the speed. I encourage listening to the episodes with Professor Falk, Kurt Roloff, Ellison Ann Williams, and later encryption-focused episodes, as well as my article on homomorphic encryption linked in the show notes. The back-end discussion regarding HTTPZ is a glimpse into a new future with yet more possibilities, a future where the internet is encrypted not just in transit, but in use. It might be a good idea to listen to Ruben Brahmanathan's discussion on social tokens after listening to this to start to understand how this all fits in together to create new opportunities. A homomorphic crypto system is like other forms of public encryption in that it uses a public key to encrypt data and only allows the individual with the matching private key to access its unencrypted data. What sets it apart from other encryption is that it uses an algebraic system to allow a variety of computations or operations on the encrypted data, thus encrypting data in use. Homomorphic describes the transformation of one dataset into another while preserving the relationships between the elements in both sets. It derives from the Greek homo, meaning the same, morphic, meaning structure. Data in a homomorphic encryption scheme retains the same structure. Identical mathematical operations, whether they are performed on encrypted or decrypted data, will result in equivalent results. So let's get into some further translations for this episode. At a high level, BGV, BFV, CKKS are all different forms of schema within one branch of homomorphic encryption that Rand refers to in this episode as leveled homomorphic schemes. TFHE, or the bootstrapping branch, is based on an algebraic construct that allows large finite fields to be represented compactly in fewer bits. That construct is known as the torus construct. So what do all these acronyms stand for? The cryptologists who devised these constructs, like BGV, BFV, CKKS, and in the case of TFHE, as I said, it means torus fully homomorphic encryption, which for the purposes of this podcast is the algebraic construct that enables bootstrapping. Now, Zama has improved on TFHE, and this has important implications for a number of use cases. And one of the most exciting is that it can be used to homomorphically encrypt the neural networks that are the backbone of machine learning and AI. Now, let's break this down at a high level, and don't shoot me for painting with a broad brush. Machine learning is a subfield of artificial intelligence. We talked about that a bit in our episode with Igor Mezek of Mixmode. Deep learning is a subfield of machine learning, and neural networks make up the backbone of these deep learning algorithms. Neural networks mimic the human brain through algorithms based on, at a simplistic level, 4 primary components: inputs, weights, a bias or threshold, and an output. Larger weights means greater importance, and thus it makes a single input's contribution to the output more significant compared to the others. If a node is above a specified threshold value, that node is activated. And once activated, it sends data to the next layer of the network. Otherwise, no data is passed along to the next layer, within which there are still more nodes. Now imagine the above process being repeated multiple times for a single decision, as neural networks tend to have multiple hidden layers as part of a deep learning algorithm. Each hidden layer has its own activation function, potentially passing information from the previous layer into the next one. Once all the outputs from the hidden layers are generated, then they are used as inputs to calculate the final output of the neural network. So with all that as a backdrop, I give you our episode with Rand Hindi from Zama.ai. And of course, if you like the show, please leave comments, share it with your friends. Enjoy this episode. Welcome to the Encrypted Economy, where we look at the business of, regulation, and security for all things encrypted, digital assets, blockchain technology, privacy, and smart contracts. Hope you'll join us while we explore these forces that are shaping the economy.
This is Eric Hess with the Encrypted Economy. I'm so excited today to have Rand Hindi on the show. Rand is the founder and CEO of Zama.ai, and he will be cluing you all in on his background. This is another episode in our series relating to homomorphic encryption and privacy-enhancing technologies, which we all know the encrypted economy is focused on, among other things. The funny story today is I actually found out Monday morning that it's true story, the newest Corvette, known as the American Ferrari, finally got signed by the designer. The founder signed this car. And so part of it was that we were going to drive out there and drive this back with my 17-year-old son, just because it's a cool father-son thing to do. But we were planning on doing it in the future. So Monday morning, I wake up and I'm like, oh my God, I have to change everything so I can go pick up this car, because there's a whole story behind that. So we literally do a one-way car rental. I find something in Cleveland, Ohio on the fly just to make sure. And I'm like, I got to make sure I got good Wi-Fi and everything else. So we drive up here last night. And so this morning I brought my microphone arm and I'm doing it off of a laptop that I haven't used in like a year. And I'm like, there's background noise, but in a whirlwind, I'm like, you know what? I want to do this episode with Rand. I don't care. I'm going to make it happen. I'm not going to postpone it. So this is the Encrypted Economy, broadcasting from Cleveland, Ohio, before I go and pick up this Corvette that obviously I'm also excited about, but it's just sort of a weird story. Just here I am doing my podcast from a place within the last 24 hours. I would never envision that I was going to be doing this from Cleveland, Ohio. Listen, no offense to Cleveland, Ohio, it wouldn't be my number one choice, but hey, we're going with it. So anyway, all that little background story hopefully just accentuates the fact how excited I am to have Rand on the show and do this episode. So Rand, with that, this isn't about me or picking up a car or Cleveland, Ohio. This is about Zama.ai and your story. So with all that being said, super excited to have you on the show. Why don't you introduce yourself, give us a little bit of background, and let's start getting into it.
Great story, Eric. Thank you for having me. I've actually never been to Cleveland, but I do like Ohio. So hopefully you're gonna enjoy it a little bit. I've been a developer since I was a kid. Actually built my first company as a teenager. Got into machine learning. Did a PhD in machine learning 15 years ago, and it was always very clear to me that privacy was going to be a major topic. I built a company in machine learning focusing on privacy that got acquired a little bit over a year ago. And I've been also teaching on the business of privacy and artificial intelligence at university here in France. A year ago, I started Zama with Pascal Payet. So Pascal and I have been friends for a few years when I discovered homomorphic encryption. And he came to me during the acquisition of my company saying, hey, I discovered some new stuff. I'd like to build a startup in homomorphic encryption. Do you want to do it together? I was like, damn, I don't know. I'm kind of burnt out of the acquisition of my previous company. I was going to do the whole, exit your company, take a year of a holiday kind of thing. But then how often do you get an opportunity to solve some of the biggest privacy challenges, building a company with one of your friends who's also one of the top researchers in that space? I'm like, you know what, let's just do it. So a week after I sold my company, we started Zama. And
wow.
So, yeah, it was back to back. There was no interruption.
Kept it fresh. Excellent. And so, that's really exciting. That's just shows the entrepreneurial flair. And so as we turn the corner and start to look at some of the things that you're doing with Zama, do you want to just sort of give us a little bit of background in terms of the different branches of FHE and how it sort of evolved into where it is and what you're doing today with Zama?
Homomorphic encryption, this idea that you can compute on encrypted data, is really not something new. The first time people talked about homomorphic encryption was in the 70s. Pascal, my co-founder, invented the first homomorphic addition scheme back in the 90s. And since then, it's been mostly two branches dominating homomorphic encryption. One, which is the BFV slash CKKS branch, which we call the leveled homomorphic schemes. The idea is that you can do very fast operations, additions, multiplications, but you can only do very few of them because every time you do an operation, there is noise that gets added to the data. If you do too many of them, the noise basically overflows on the data. So this branch is all about how many operations can you cram in your noise budget. The other branch, which we call the bootstrapping branch, on which TFHE is the most modern scheme, goes the opposite direction. What it says instead is, well, let's not worry about noise. Instead, what we will do is whenever the noise grows past a certain threshold, we stop, we clean up the noise, and then we can keep on going with computation. So the advantage, of course, is that you can keep on going forever. The problem is that you now have this extra overhead of doing this bootstrapping, this cleanup operation. And so for a very long time, homomorphic encryption was effectively a trade-off between limited operations that are fast or unlimited operations that are slower. This is basically no longer the case. So what we have at Zama is an extension of TFHE. So we took TFHE and we went beyond that. And we basically added two important things. First, we added a new operation called programmable bootstrapping. We can talk about that in a bit. And we also added the capability to do some leveled operations. So we took ideas from CKKS and BFV that we've added to TFHE, on top of which we've also added a new operation called programmable bootstrapping, which basically means that we now have a solution that gives you the convenience of doing unlimited computation with much, much, much better speeds than anything else that was possible before.
And then did either the earlier versions or the later versions of FHE, did they leverage programmable bootstrapping, but maybe not to the same extent you are? Or would you
Absolutely.
make a distinction between?
To explain what programmable bootstrapping is, when you're bootstrapping to clean up the noise in a ciphertext, you can consider that to be kind of like dead time, right? You're just basically not doing any computation, so you're wasting cycles. We found a way to implement an idea that's not new, it's pretty old, called programmable bootstrapping, where at the same time as you're cleaning up the noise, you're computing a function on the encrypted data. So what you get as an input of your bootstrapping operation is an encryption of X, and what you get as an output is an encryption of f of X with the noise reduced to the minimal amount. So you're basically getting for free the ability to compute an arbitrary function on the ciphertext. So this idea actually came from the original TFHE, because the original TFHE was using bootstrapping to compute Boolean functions. Boolean operators, basically. We've just extended this concept to be able to compute arbitrary functions on integers and real value data.
Interesting. So yeah, so and it seems like an area that you contemplate growing even more for Zama.ai, right?
Absolutely. Programmable bootstrapping is important because it gives you a very efficient and fast way of evaluating something like a nonlinear function. So whenever you have a function that is basically not a simple, polynomial or something like that, there is no easy way to compute that homomorphically. With programmable bootstrapping, you can encode that function in the bootstrapping operation, and basically in a few milliseconds, you can get the result of applying it. So now, think about this in the context of something like machine learning. In a neural network, there is something called an activation function. Every neuron takes as an input the previous neurons, and that goes through a special nonlinear function called an activation function. This is precisely what creates the ability for the network to learn the patterns. If you remove the activation function, there is nothing really you can do with a neural network. There was no efficient way of computing that in the past. With programmable bootstrapping, every neuron basically programs the activation function and does a bootstrap and produces the output of the activation. So not only can you compute those activation functions, you can also go as deep as you want because the ciphertext never gets noisy. Every neuron outputs a clean ciphertext. And so that's how we're able now with the technology we have, to evaluate 100-layer deep neural networks with real activation functions, something that was not even possible to think about just a year ago.
Wow, that's really exciting. And how does this all relate to the FHE libraries? Because there's a number of them out there, and maybe you could comment on how they're used and what's the differences and how like the listeners should contemplate them?
FHE Library is really just an implementation of a homomorphic scheme. And to be clear, that the technology, the variant of TFHE that we built at Zama is not specific to machine learning. It just turns out that it's very useful for machine learning. But we implemented it in a generic purpose homomorphic encryption library called Concrete. Concrete effectively is, if you want, a TFHE library that has all of the added capabilities that we offer with Zama's technology. If you compare it, for example, to Microsoft Seal, which is a very popular library, Seal is really mostly focused on BFV, BGV, CKKS, just like Palisade. They do some work around TFHE, but I would say that Concrete in the next 6 months is going to become the most advanced and feature, let's say, complete implementation of TFHE, and is going to be definitely the only library that includes things like programmable bootstrapping, things like the level TFHE operations, and so on and so forth.
For your average user's experience, what does that mean? Like if I'm a company and I'm thinking about implementing homomorphic encryption for whether it's machine learning or for some other tasks, let's just say it could be AML is a very popular one. What does this mean for me, Zama's additional capabilities?
When you want to implement a homomorphic program, usually what happens is you have to create some sort of circuit, a graph of homomorphic operations. If you want to use the original version of TFHE, your graph is just going to be a Boolean circuit. So every node is going to be effectively a Boolean gate. If you're using CKKS or BFV, every node is going to be an arithmetic operation, a multiplication or an addition. With Zama, because we've got this new idea of programmable bootstrapping, some of those nodes could actually be functions themselves that you evaluate on the ciphertext. And so rather than representing your program as an arithmetic circuit or as a Boolean circuit, you can represent it as a functional circuit, a combination of additions, multiplications, and functions on the ciphertext. And this, in fact, when you think about it, is just like a neural network. So a neural network is just a very specific, well-structured example of a functional circuit. It's additions and activation functions. You can generalize that to any kind of program. So it turns out that functional circuits are effectively a new paradigm for programming homomorphically that is easier to understand for a developer because you're no longer thinking in terms of addition multiplication, you're thinking in terms of combining functions.
Okay, I understand that. So let's just play that out just a little bit more. What kind of, what are the immediate capabilities, the immediate opportunities you see with that, additional capability?
Machine learning is a pretty obvious one. Because the ability to represent a neural network as a functional circuit and compute those activation functions means that we can take an existing network that you're already using in your product, and without you having to change anything about it, we can convert it into a homomorphic neural network that can do encrypted machine learning effectively. This is really, really important because thinking about adoption, the easier it is for someone to bridge between non-encrypted and encrypted worlds, the more likely they are to be using your technology. And so beyond the library, beyond Concrete, beyond the crypto itself, we're also working on providing tools for people to do that as effectively as possible, even if they know nothing about a homomorphic encryption. So the way this works is very simple. There is a compiler. The compiler takes your neural network as input, produces an optimized, secure functional circuit as an output, and then you've got Concrete that can run it on your server, and you're done, and that's it. There is nothing you need to think about in terms of manually writing your circuit. You just give your neural network as an input, and you're running the output of the compiler in Concrete, and that's it.
Wow, yeah, that is exciting.
Super easy.
Yeah, and that additional capability, it could really change the way that homomorphic
everything.
Yeah,
everything, right? I mean, think about it. Like, let's take an example. Let's take facial recognition. Facial recognition is a very, very sensitive use case. Sensitive because people don't really like their faces, to be floating around the internet, but also because whoever wants to authenticate someone based on their face has to also keep a database of passports or some kind of like proven biometric templates. This database is extremely valuable for someone who wanted to steal this data. With homomorphic encryption, you could keep an encrypted database of biometric templates, and you could do encrypted facial recognition against the database. So even if a government or a hacker has access to the database, they would not be able to get people's faces. In fact, they would not even know who you're authenticating against this database. So I think, this is an application that's just not possible without something like programmable bootstrapping, because the functions you need to compute just cannot be done efficiently with existing technologies. You need the additional capabilities that we're building at Zama to make that practical for real.
Right. I also see it very valuable in the context of regulation, where you have regulators who are consuming a lot of order data across different markets and creating computations. And as regulators collect more and more data, it's an Achilles heel for the marketplace, because if somebody is able to hack into that, they can get all kinds of information. With programmable bootstrapping, you start to position yourselves to be able to take on that marketplace, which is intriguing, as well as the traders themselves who probably love this.
Absolutely. I mean, you could do homomorphic fraud detection. You could do homomorphic medical diagnosis. You could do homomorphic genetic analysis. You could do, homomorphic speech recognition. Why would you put a microphone in your house that's connected to some company if you can do that encrypted? Like, there's so many use cases that for me, it's pretty obvious that at some point, once homomorphic encryption gets fast enough and easy enough to integrate, it will become a standard. That will become the way that people protect applications in the cloud, because your value as a company is not the data of your users, is what you do with the data of your users. And homomorphic encryption precisely solves that problem by enabling you to do something with the data without actually having the data itself.
Right.
You remove the liability of getting hacked effectively.
And one point that when we had Ellison and Williams from Enveil on the show, she brought up is how it doesn't require this whole taking your existing data or your existing programs and converting them. You can basically just apply that framework on top of existing databases, and it'll run. So it'll consume the existing databases. You don't have to worry about sort of, and that's sort of one of the beauties of homomorphic encryption, is it works with existing legacy systems to some extent, right?
Absolutely. I like cryptography in general. Multi-party computation typically is very difficult to put in production because it does require shifting from a server talking to a client to a distributed system. That's the same level of complexity as moving from a simple database like an SQL database to moving to a blockchain as a database or something like that, right? Homomorphic encryption doesn't require changing your engineering system. You're just now adding a layer of encryption on top of it. And so that's why, to me, it's pretty obvious that it's going to be the dominant technology. And I know, and I can guarantee you that at some point, once this is standardized and is fast enough, it will become the basis, perhaps even for a new internet protocol. The same way we move from HTTP, where nothing was encrypted on the internet, to HTTPS, where data that's being sent is encrypted, we can now move to like HTTPZ, where data is encrypted end to end, even during processing. And when that happens, when you can guarantee privacy at the protocol level, then people will no longer have to worry about it, not because it doesn't matter, but because it's no longer going to be an issue. And this is really why I'm looking forward to homomorphic encryption. We need to build this HTTPZ protocol for the future of the internet to be safe.
Right. No, it's very exciting because, you hear a lot about Web 3.0 and what it means for the internet. And it actually, part of the vision of 3.0 is to empower the users more with their own data. But how can you really give that power to the users? How can the users be secure with their own data going online for transactions or their personal information or digital identity tokens if they don't have that additional layer that protects the data in use? And as you start to move towards sort of that post-quantum world where The malicious actors are getting better, and the current infrastructure just isn't going to support it. I mean, it's 100% clear. So the timing of HTTPZ and what you're doing is not only something that's a nice to have, but it's going to be desperately needed as malicious actors in the post-quantum world advance their own decryption capabilities and malicious tools.
Absolutely. I think privacy by design is how we should build things now. And HTTPZ as an idea is effectively privacy by design at the internet protocol level. We just cannot trust the servers anymore. It's not just about people listening to the network traffic. It's also about the people doing the computation. Those servers now can be compromised. They can be compromised by hackers. We've seen many data breaches. It can be compromised by governments, local or foreign governments who want to engage in mass surveillance. They can be compromised by a rogue engineer in the company. And I know the companies are doing their best to prevent that, but the forces behind it are so strong that the only way to guarantee it cannot happen is to not have anything to steal in the first place. Just get rid of the data. Data is a liability. If you keep it encrypted, there is no longer an incentive for people to access your servers, right? It's really that simple. Keep everything encrypted all the time. It won't prevent you from building your business. It won't prevent you from offering your services. It'll just basically remove your responsibility in securing the privacy of your users.
Right. And so as the pathway to get to HTTPZ, what has to happen for that to occur in a real sense?
You really need three things. It's very simple. You need technology that works. That's done. We have it. It's going to get faster and faster, but at least it works. It's now just a question of improving performances over time. We are going to get there. There's going to be a Moore law of homomorphic encryption in terms of latency and computing power needed to make it happen. The second thing you need is standardization. If people do not agree on how this works, you are not going to have a protocol. Standardization is happening right now. And people are looking at standardizing both, BIV CKKS as well as TFHE. So I think in the next couple of years, we will have sort of a settled agreement on which technology people can start integrating in production. We want to be the company representing TFHE. If you want to use CKKS, use Microsoft's library. If you want to use TFHE, use Zama's technology. That's effectively how we're thinking about that. And finally, the third step is you need people to use it. You need awareness. And I believe that in 2021, the only way to create mass adoption for a technology like that is to make it completely open source. So everything we do at Zama, the whole business is built around being open source. Everything we do, we open source and we publish because we want as many people as possible to put their hands on this technology, to experiment with it, to integrate it, to feel comfortable using it, so that eventually it just becomes very commonplace. For us, open source, standardization, and performance are the three key things that needs to happen in order for this to become a reality.
You want to talk a little bit about the AI framework?
So the first thing we released is Concrete, our FHE library. This is available. You can use it. You can go to our GitHub. You can find it there. You can play with it. But it is meant for cryptographers. If you're not a cryptographer and you do not know homomorphic encryption, it's pretty difficult to use as is. So that's why we're building a framework on top of it to automate homomorphic encryption in machine learning workflows. So that framework is composed of a compiler that converts your network into a homomorphic program, a functional circuit, and effectively what's kind of like a virtual machine that executes this homomorphic circuit on whatever infrastructure you have available. We're abstracting away the complexity of the cryptography by exposing machine learning, data scientist-friendly APIs in that framework. This is something we're working on. We're going to be open sourcing it in the coming months. It's a very, very difficult piece of technology. It turns out that compiling a neural network is challenging task, I would say, but it's precisely why it's so interesting. It's precisely what makes it important as well, right? If the compiler is a hard thing to do, imagine doing it by hand. It's really non-trivial. But I do believe that this is going to be a major kind of like unblocker for the machine learning community. Imagine you're a data scientist and you no longer have to worry about understanding cryptography. You can just use that, convert your existing machine learning models into homomorphic equivalents, and just be done with it and put it in production. It should be really that simple.
And the AI framework, is that designed to sort of basically optimize, whatever you apply the FHE to? Meaning if you upload it to this virtual server, it'll make the necessary adjustments to make it more efficient, and sort of, is that sort of the framework for the AI component? Like what changes today versus when you have the AI framework in place?
So the way that this works is you give it a model, a network, you give it a validation set. So some data that it can validate the new homomorphic program against to make sure that you're not losing accuracy, that it's still behaving as expected. And you're giving it effectively a target hardware cluster. Do you have GPUs? Do you have CPUs? Things like that. And based on all of this, it will automatically optimize all of the homomorphic parameters so that you're getting the best trade-off between your desired accuracy and the runtime performances on your hardware. And that's precisely what's so difficult, is that you're effectively doing a multi-objective, optimization in, a very high dimensional space. Really not trivial, but, it is a problem that is, I would say, understandable in terms that we're familiar with. It has never been done. Homomorphic compilers traditionally were really about taking a C++ program and executing those Boolean gates using TFHE, for example. This is really not what this is. This is a compiler that takes a statistical program and converts it into a homomorphic statistical program, right? It's not about doing the bits homomorphically. It's about keeping the behavior of the original program, but in a completely different space. You've got Concrete, which is the sort of like low-level FHE library. You can already use that today. On top of that, we're building multiple different frameworks, starting with machine learning. But the next step is to build a framework, for example, for databases, converting an SQL program into a homomorphic SQL program, and creating frameworks for all kinds of traditional workflows that people have in the cloud where data might be sensitive. So it's just that machine learning is such a low-hanging fruit for our technology that we decided to focus on that. But our technology could be used to build frameworks for anything. The framework is really just the encapsulation of all of the features necessary for a particular use case. It has nothing to do with homomorphic encryption. You're just basically building a different compiler for every one of those use cases. That's it.
Okay. So in other words, you're kind of contemplating both the application of the FHE, but also the optimization of the underlying databases or applications associated with it.
Absolutely. It's all about ease of use. The easier we make it for developers, the more likely they are to use it. And that's why we're taking this approach of having frameworks for everything. So if you ask me, what's the long-term plan for the company, we want to be the technology that people use to secure cloud computing, period. We want to be the technology that eventually becomes, this HTTPZ protocol. And the only way to do this is to make this as easy and as widely available as possible. We frankly don't really care that people use it for machine learning or databases. We just care that people stop doing unencrypted computation in the cloud. Things should be encrypted end-to-end at all time, period. That's our goal. Make that possible. And as a developer, as a company, we want to provide the tools for you to do that as effectively and easily as possible.
Once somebody has done the encryption in the cloud, fully implemented the homomorphic encryption, what do you see as now building on top of that? What's the vision on top of that? Is that too challenging of a question? Because once you've done that, once you've established that, because we had, in some of our earlier episodes, I think Kurt Roloff from Duality, he said, my mission is to make homomorphic encryption boring. It wasn't the catchiest title, but what he was really saying is it shouldn't be something, and I think everybody is sort of saying has the same objective, which is at the end of the day, right now there's encryption at rest, there's encryption in transit, and obviously the gaping hole, the massive gaping hole, is encryption in use. So once we sort of built that, like nothing really stops there, right? There's always the next, there's always what you can build on top of it and how you can continue to improve and enhance. And I know this is going maybe far beyond what even, because obviously there's a huge lift to even get to that place where we're at HTTPZ, right? And where it's being implemented. I mean, there's still a knowledge gap. There's still an acceptance gap. Most people hear the words homomorphic encryption and their mind just instantly goes blank. And then they have to reorient themselves like, okay, it's encryption, but what is this, And so, there's still a lot of education that we have to do, which is one of the things that honestly, that this podcast is trying to do. Mm. And I'm taking it, so for those who have hung around and sort of now get it, what is the next layer that gets built on top of that?
I think we don't really care this called homomorphic encryption. It's just end-to-end encryption. And homomorphic encryption is the opportunity to generalize end-to-end encryption to more than just transmitting data, effectively. I don't think that people are going to say that word homomorphic encryption in 10 years. I think people are going to say end-to-end encryption. And HTTPZ is going to be the end-to-end encryption protocol for the internet, just like HTTPS is the encrypted transmission protocol for the internet. It's going to be really that simple. And I believe that if we get to that point, if you get to the point where every web service has an HTTPZ URL that automates this process for the user, you're done with privacy. Like, it's no longer a question of privacy. And to be clear, privacy for me means access to the data. Is protecting access to the data, which is not the same as ethics, which is what is acceptable use of the data. Because homomorphic or not, you could still misuse the data. Even if you don't know what you're doing, you could still use the data in the wrong way. But this is not something you solve with technology. I think the real questions beyond privacy, beyond homomorphic encryption, are going to be questions around what can and what should we let people do with all of this data. This is a cultural question. This is a regulatory question. GDPR is just scratching the surface of what we need to think about. I'm concerned about identity. I'm concerned about deep fakes. I'm concerned about homomorphic deep fakes, right? But one thing is for sure is that nobody will be concerned about privacy in 10 years. That will be done. That will be solved. And we can move on to other topics.
Right. Does homomorphic encryption, to some extent, could it also be used to limit? I mean, obviously maybe not today, but the deep fakes. I mean, if I'm a trusted news source, for example, to the extent that I'm encrypting end to end, and the user can decrypt on an end to end basis, then presumably that provides a degree of authenticity, particularly if it's on HTTPZ. I mean, maybe an extended vision of HTTPZ would facilitate the ability to authenticate the source from an end-to-end perspective that hasn't been corrupted. Or do you think do you think it's not really within that realm? It has to kind of be addressed differently.
Actually, interestingly enough, I think that traditional HTTPS would do a better job at that, because the server has to prove that is the right recipient and sender of data with the user. With HTTPZ, the server doesn't have any keys it's using. The user is the only one encrypting and decrypting. So the user has a key, but that's it. I think there is an interesting challenge around proving the authenticity of what just had been done on the server. And probably this is going to require other cryptographic technologies, zero knowledge proofs, for example, or something like that. So maybe the next step, beyond privacy for the user, is guaranteeing that what was done with the data is what was supposed to be done with the data by the right person. So yeah, zero knowledge proofs, authentication, mixing them up with homomorphic encryption is going to be an incredibly interesting topic.
Interesting. Well, this was a great discussion. I'm so excited to have had you on the show, and definitely seems like you're doing something very different, very, sort of reaching into the next level of computational power for homomorphic encryption. I mean, it's great to see it advancing and seeing what you're tackling. So, I mean, thanks so much for joining the show. Definitely keep us updated as things change. We'll definitely get it out to the listeners and make sure they're up to speed. Anything to note on closing?
All good. Thank you for having me, Eric. Like your podcast. I hope people are going to enjoy. And maybe just one final thought. We talk a lot about the potential for homomorphic encryption, as if this was something far away in the future. I think it's much closer than people realize. 2021 is the year where we build the first real use cases with homomorphic encryption. And that's going to be a turning point in adoption. So it's going to be a lot faster than people think. If you are thinking about homomorphic encryption and believe that this is 10 years in the future, you should rethink your strategy because it's happening now. It's really happening now.
Excellent. Well, it's exciting stuff. Once again, thanks so much for joining the show, Rand.
Thank you, Eric.